Welcome to the video lecture for section 4.2. This is addition rule and multiplication rule. This is for statistics, STA 2023. My name is Jorge Young. So in this section, we're going to present the addition rule as a tool for finding the probability of two events, or the probability of A or B, which is the probability that either event A occurs or event B occurs, or they both occur as a single outcome of a procedure or a trial. The word or in addition rule associated with the addition of probabilities. So in this section, we'll also present the basic multiplication rule used for finding the probability of A and B, which is the probability that event A occurs and event B occurs. Now, the word "and" in the multiplication rule is associated with the multiplication of probabilities. So first thing, a compound event. A compound event is any event combining two or more simple events. We spoke about simple events in the previous lecture. So the notation for addition rule is the probability of A or B is the probability of a single event trial. Event A occurs or event B occurs, or they both occur. Now, to find the probability of A or B, we're going to add the number of ways event A can occur and the number of ways that event B can occur, but add in such a way that every outcome is counted only once. Now, the probability of A or B is equal to the sum divided by the total number of outcomes in the sample space. So in other words, the formal addition rule for the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, where A and B denotes the probability that A and B both occur at the same time as an outcome in a trial. And so one example that I like to give is, what is the probability of choosing that you have a deck of cards? So what's the probability of choosing a queen or hearts? And so if we say A, it's the probability of choosing a queen, B is the probability of choosing hearts. So we're going to go ahead and add the probability of choosing a queen from a deck of cards to the probability of choosing a heart from a deck of cards. But then we have to subtract the probability of choosing the queen of hearts. And the reason being is because if we don't, it's double counted. Now you got to remember that the queen is included in the probability of queens and also the probability of hearts. So one of those has to be eliminated. And so that's why we subtract the probability of A and B. Another thing I want to say about the probability of A and B is that those two events, whatever happens, has to happen at the same time. In this example, in order for it to fit, it has to be the queen of hearts. The next thing we're going to talk about is disjoint events in the addition rule. So disjoint or mutually exclusive events A and B are disjoint or mutually exclusive. They cannot occur at the same time. And so two examples of that would be a full-time student and a part-time student. You can't be both simultaneously, right? You're either full-time or part-time. So disjoint events: event A, randomly selecting someone for a clinical trial who is male. Event B, randomly selecting someone for a clinical trial who is female. So the selected person cannot be both. Now, events that are not disjoint: randomly selecting someone taking a stats course and randomly selecting someone who is a female. So here's a summary of some of the key points. To find the probability of A or B, you first associate the word "or" with addition. To find the value of P, the probability of A or B, you're going to add the number of ways that A can occur and the number of ways that B can occur, and be careful not to double count. The next thing is complementary event and addition rule. So we use A hat to indicate that event A does not occur. So common sense dictates this principle. We're certain with a probability of 1 that either A occurs or it does not occur. So it follows that the probability of A or the probability of A hat is equal to 1. Now, because events A and A hat must be disjoint, we can use the addition rule to express this principle as follows. The probability of A or A hat, or the probability of A or the complement of A, is equal to the probability of A plus the probability of A hat, which is the probability of A not occurring, and that has to equal 1. So here's, again, just doing some algebra. All of these are equal to each other. So here's an example: sleepwalking. Based on a journal title, the probability of randomly selecting someone who has sleepwalk is 0.292. So the probability of sleepwalk is equal to 0.292 based on the data from this journal article. Now, if a person is randomly selected, find the probability of getting someone who has not sleepwalked. And so we're going to use the rule for complementary events. So the probability of someone has not sleepwalked is equal to 1 minus the probability that someone sleepwalk, which is 1 minus 0.292, which is 0.708. So the probability of random selecting someone who has not sleepwalked is about 70.8%. So some notation, the probability of A and B is equal to the probability that event A occurs in the first trial and event B occurs in the second trial. The probability of B given A, this is what they call conditional probability, represents the probability of event B occurring after event A has already occurred. So intuitive multiplication rule, to find the probability that event A occurs in one trial and event B occurs in another trial, we multiply the probability of event A by the probability of event B. But we have to be sure that the probability of event B is found by making the assumption that event A has already occurred. And so the formal multiplication rule, the probability of A and B is equal to the probability of A times the probability of B given A. So let's talk about independent events. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. So if A and B are not independent, they're said to be dependent events. So here's an example, screening drugs and the basic multiplication rule. So 50 test results from the subjects who use drugs are shown below. Positive test results 45, negative test results 5 for a total of 50. If 2 of the 50 subjects are randomly selected with replacement, find the probability that the first selected person had a positive test result and the second selected person had a negative test result. And then for B, repeat part A by assuming that the 2 subjects are selected without replacement. Now, with replacement means the first selection with 45 positive among the 50, so the probability of a positive result would be 45 over 50. The second selection, we got 5 negative, 50 total, so the probability of a negative test would be 5 out of 50. So with replacement, what happens is that our sample space remains 50. And so now we can apply the multiplication rule, and so it's 45 over 50 times 5 over 50, so we get a 0.09%. Or about a 9% chance. So without replacement. Without replacement of the first subject, the calculations are the same, the mathematics is the same, except that the second probability must be adjusted to reflect the fact that the first selection was positive and now is no longer available for the second selection. So after the first positive result is selected, we have 49 test results remaining and 5 of them are negative. So the probability of the second one being negative would be 5 over 49 because there are no longer 50 results. So the probability the first selection is positive and the second is negative without replacement is 0.0918. So it's slightly different than the first one, which is 0.09. So in the world of statistics, sampling methods are critically important and the following relationships hold. Sampling with replacements, the selections are independent. And the reason they're independent is because the sample space does not change. Sampling without replacement, they're dependent, and that's because the sample space has changed. In other words, if I'm sampling without replacement and I have a deck of cards and I choose the first card and I don't put it back, well, I no longer have 52 cards to choose from, I have 51 cards. So the fact that I selected the card first and then not replace it has changed the probability of selecting the next card. The next thing we're going to talk about is the 5% guideline for cumbersome calculations. Now, we're sampling without replacement, and the sample size is no more than 5% of the size of the population. We can treat the selections as being independent, even though they're actually dependent. So assume that 3 adults are randomly selected without replacement from the 247,436,830 adults in the United States. Also assume that 10% of adults in the U.S. use drugs. So find the probability that 3 selected adults all use drugs. So, because the 3 adults are randomly selected without replacement, the 3 events are dependent. But here we can treat them as being independent by applying the 5% guideline for cumbersome calculations. So the sample size of 3 is clearly no more than 5% of the population of almost 248 million. So then we get the probability of all 3 adults use drugs is the probability that the first one uses drugs, and the second one uses drugs, and the third one uses drugs. So it's going to be the probability of the first uses drugs times the probability of the second uses drugs times the probability of the third uses drugs, which is 0.1 times 0.1 times 0.1, which gives us 0.001. So there's a 0.001 probability that all 3 selected adults use drugs. The next thing is the principle of redundancy. This is used to increase how reliable some systems are. So our eyes have passive redundancy in the sense that if one of them fails, we continue to see. An important finding of modern biology is that genes in an organism often work in place of each other. So engineers often design redundant components so that the whole system will not fail because of the failure of a single component. So modern aircraft are now highly reliable, and one design feature making a contribution to how reliable they are is what they call redundancy, whereby critical components are duplicated so that if one fails, the other one will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems. So if any one system fails, full flight control is maintained with another functioning system. So for this example, we're going to make the assumption that for a typical flight, the probability of a hydraulic system failure is 0.002. Now, if the Airbus 310 were to have one hydraulic system, what is the probability that the aircraft flight control would not work? Given that the Airbus 310 actually has 3 independent hydraulic systems, what is the probability that on a typical flight, control can be maintained with a working hydraulic system? So for A, the probability of hydraulic system failure is 0.002, so the probability that it does not fail is 0.998. That is, the probability that flight control can be maintained is as follows. The probability that one hydraulic system does not fail is equal to 1 minus the probability of failure, which is 0.998. Now, with 3 independent hydraulic systems, flight control will maintain if the 3 systems do not all fail. So the probability that all 3 hydraulic systems failing is 0.002 to the 3rd power, because there's 3 of them. So you can see it's a really small chance. Now, it follows the probability of maintaining flight control is as follows, which is 0.9999992. So it's almost 1. So how do we interpret this this information? With one hydraulic system, we have a 0.002 probability of failure. With 3 independent hydraulic systems, there's only a very small probability that flight control cannot be maintained because all 3 systems failed. So by using 3 hydraulic systems instead of 1, the risk of failure is decreased not by a factor of 1/3, but by a factor of 1 over 250,000. So by using 3 independent hydraulic systems, risk is dramatically decreased and safety is increased. So last few things. Addition rule for the probability of A or B. The word or suggests addition, and when adding P of A and P of B, we must add in such a way that every outcome is counted only once. The multiplication rule for P of A and B, the word and for 2 trials suggests multiplication. And when multiplying P of A times P of B, we must be sure that the probability of event B takes into account the previous occurrence of event A. And that's the end of 4.2. Thank you.